In this chapter, we will introduce pure bending. When we talk about pure bending, we consider that whenever we do a section for a certain material, along this section, it will only undergo a bending moment. So this part of the course will be devoted to the study of pure bending and of the stresses and deformation it causes. For example, if we consider as the figure below, we have an athlete holding the barbell with his hands placed at equal distance from the weights. Let us do some analysis about the process here. You have the weight of the first part here, W1. You have the weight of the part here, W2. Due to symmetry, you have that W1 is equal to W2. And the athlete will develop upward forces in order to hold the system. And for equilibrium condition, the forces applied will be equal in magnitude. And as you can see then, F and W1 will create a couple that is counterclockwise. And this couple is equal to M1 equal to F times the distance, this distance here. And of course, F will be equal to W1 for equilibrium purposes. And you have also that this F and W2 will produce a clockwise couple, M2 equal to M1. So because of the symmetry in this figure, you have the forces developed will be equal, and each one will oppose one of the weights, and each force will create with one of the weights a couple equal to F times distance between the hand and the body. Okay, so now if you do the analysis of this problem, if you take any point between the two hands of the athlete, then in this section here, if you do this analysis of internal forces and bending moments, you will get that you just have a bending moment. If you remember from statics, whenever you have a beam and this beam is subjected to external loads, okay, and support reactions, let's say, for example, if you calculated AY and BY, and you have, let's say, a load here, for example, a load P applied with certain distances. So you know the distance from A and the distance from B. Then you can determine at any section the internal forces and couples. So you say to determine what is happening at any section, what should I do? I should cut and remove one of the parts because by action reaction, the force of part 1 on 2 is equal to the force of 2 on 1. So let us say we removed part 2, then what we get is AY with P, and the internal forces and couples developed at the section will be present to ensure equilibrium of this part. So if you remember in statics, we determined that we can have a shear force, okay? And by convention, the shear force is positive if it's producing a clockwise moment about the end of the beam. So this is called V. You have the normal force, which is positive if it's causing stretching of this part. And you have the, the bending moment, which will be positive if it's compressing the upper part of the beam. So in this problem, if we do a similar analysis at any point between the two hands, then we'll get that we'll just have a couple moment developed. Why? Because, for example, let us consider this section. Then if we present this section, what do we have? We have, let's say, the weight, W1. We have the force of the hand here, upward, equal to W1. and you have a distance A between these two forces, or D. Then when you do a cut at the following section, first, if you write sum of x equals to 0 on your part in equilibrium, you don't have any axial load acting. This is why you don't have a normal internal force. So N is 0. Now concerning the shear, so the convention for shear is to be positive downward here. If you do sum of forces along y equals to 0, you have, considering the positive direction downward, you have plus W1, so plus W1, and minus F, which is equal to W1, plus V equals to 0. So also the shear is 0. So at this section, no shear. And finally, for the bending moment, it's the only one which will not be 0 here, because the bending moment should oppose the couple created by the weight and the force of your hand. Okay, so you can say that sum of moments equals to 0. Let us consider the positive direction of the equation as counterclockwise. So you have plus m plus your bending moment. And since you have that the couple created by F and W is counterclockwise, so it's plus F times D equals to 0. Therefore, your bending moment will be a negative value because it should be clockwise to oppose the action of the counterclockwise moment created by W1 and F. So you deduce that M is minus FD. So your bending moment here in this section is clockwise, okay? And this is what we call pure bending. Whenever in a section of interest, you just have a bending moment developed without any other internal forces, then this is pure bending. And we'll see together in this chapter that pure bending, this bending moment will be due to a certain distribution of normal stresses. And together we'll derive the expression of normal stresses and the curvature of the section, which will result from pure bending. So this is one of the main objectives of this chapter. Now, here we can see the example we talked about. So let's say we give some numerical analysis. So let's say the weight here, you have a weight of 80 lb on A and B. You are developing upward forces at C and D. You can easily determine as you can just say due to symmetrical effects and equilibrium condition, I should have RC to be equal to 80 and RD equal to 80. If you didn't pay attention for the symmetrical effects, it's fine. You can just say, I have RC and RD as unknown, and I want to solve for these values. So you need to write two equations of equilibrium for your beam or your part AB. So you can say that the first equation is sum of forces along Y equals to 0. So you have minus 80, if you consider the positive direction positive, the y direction positive upward, you have minus 80 plus RC plus RD, and minus 80 equals to 0. So you deduce that the first equation relating RC and RD is that RC plus RD should be equal to 0, sorry, 260. So this is the first equation relating RC and RD. Now, if you want to find the value of RC, you can, for example, say, let me do sum of moments about D. Because if I do sum of moments about D, RD will not have any moment since it's passing by point D. So I just can determine from this equation what will be the value of RC. So the second equation you can write is sum of moments about d equals to 0. You consider any positive direction you want. Let us say you want to have the counterclockwise direction as positive. So you have in this figure, ATLB is producing about d a counterclockwise moment. So it's plus 80 times the distance from the force at A to D is equal to 12 plus 26 equals to 38. Now, concerning RC is producing about the clockwise moment. So I just have to do minus RC times 26. And finally, the ATLB force also is producing about the clockwise moment. So it's minus 80 times 12 because the distance from ATLB to D is 12 inch. So now this equation will obviously give you that RC is equal to 80. And when you replace RC by 80 in equation number 1, you get that RD is also 80. Okay, and then you can say that I can solve for RC and RD. Also, another easier way is to take just the middle point of your beam and say that I should have sum of moments about O equal to 0. Due to symmetrical effect, you have the moment of this ATLB will cancel out with the moment of this ATLB force. So RC and RD should have same magnitude because they are equidistant from O. So from sum of moment about O, you can get that RC is equal to RD. And since from equation 1, RC plus RD is 160, then RC is equal to RD is equal to 160 over 2. So all of these, whatever you do, you will get the same result, that RC should be equal to RD should be equal to 80. Now, if you consider portion CD of your structure, this portion is subjected to pure bending because if you do a cut at any point of this section and you do the analysis we did before, you don't have a normal force, you don't have a shear force, you just have a bending moment, okay? And also you can say that when I do the analysis of this part, I can replace the two forces at A and C by a couple that is counterclockwise equal to 80 times 12. And for this part, for dB, I can replace by a clockwise couple of 80 times 12. So now if I do the analysis, when I do a cut here and I remove this part, I should have the development of a bending moment in part CD equal to 80 times 12, which is 960, but in the clockwise direction. Okay, and keep in mind that whenever by action reaction, if you take this part, you have a clockwise couple. Now, if you do the cut and then remove the first part, you keep the second one. By action reaction, the couple will be counterclockwise. So now if you want to just illustrate what is happening in member CD, okay, you have C will be subjected to a counterclockwise couple and D will be subjected to a clockwise couple, okay, which will lead to bending effects. So to verify, you can say at D, for example, if I do this cut like this, okay, and I remove part AD, the action of part AD on DB will be a couple bending moment couple opposing the clockwise couple created on part BD. So when I do a cut and I remove AD, at D I should have a a couple opposing the clockwise one, which should be counterclockwise. Now, here, when you illustrate what is happening at D, you are removing DB. So you are taking the other part. So by action reaction, if you do a cut at D and you remove the other part, then the couple acting on D will be the inverse of this one by action reaction, and it will be then clockwise. And at C, since you removed now part AC, the couple will be the action of AC on the remaining part is a counterclockwise couple. So CD will be subjected to two opposing couples at its extremity, and then it's subjected to pure bending. Now, let us take other examples where you can encounter, let's say, bending effects. Not always, whenever you say pure bending, you only have bending. You can have other examples with bending moment and, as we said, normal force or shear force. So for example, if you consider the bar clamp example here, we have a bar clamp that exerts forces on two pieces of lumber as they are being glued together. Equal and opposite forces will be exerted by the lumber on the clamp, and the straight portion of the clamp is subjected to an eccentric loading. Why? Because here, if you look at this figure, okay, whenever you apply pressure forces on the clamp, okay, you have from this side, if we consider as system our clamp, okay, this is our clamp. The purpose here is to exert from the clamp on the system, on these two pieces of lumber. We want to exert pressure forces like this. So in order to when doing these pressure forces, we are able to create a better, if you want, adherence between the two parts, because the two parts should be glued together. Okay, so by action reaction, if you consider now your clamp, then these two pieces of lumber will exert by action reaction opposite forces on the clamp. So if my system is a clamp, then on this system I have these forces, which are by action reaction opposite to the action of the clamp on the two pieces of lumber. And then let us say, for example, that you know the load, the value of this force. It's 150 lb. Now, if you want to do the analysis in the bar clamp of this part, what are the internal forces and couples developed in this part? You can do a section. You can do a cross section here. Okay, and whenever you do this cross section, okay, then and you reject the other part, you will represent what are the external forces acting on this part. Whenever you do a cut in a section, all internal forces will become external. So now, when you apply this force here and you do a section there, then you apply just equilibrium conditions to get what are the internal forces and couples developed at this section. So of course, when you do sum of forces along x equals 0, you will get that I don't have any load, so no internal force developed along this direction. So if you want, no shear force. Now, if you do sum of Fy equals to 0, you will see that you have an axial load acting on your section, and it should be in magnitude equal to P prime, and in direction it should oppose it. So it will be downward equal to 150 lb. And also, since P, due to this eccentricity, okay, of 5 inch, you will not only have development of an axial load, but also of a bending moment at this section to oppose the counterclockwise moment created by P and P prime. This counterclockwise moment created by P and P prime is equal to 5 inch times the force of 150, which will be equal to 750 lb inch. And then the bending moment will be opposite. So since the couple created by P and P prime is counterclockwise, the bending moment at this section will be equal to 750 lb times inch. So here, with this is an example of axial loading plus bending moment developed. So it's not pure bending, it's combination of axial loading and bending. And we'll see together after how to take into consideration combined effects. So if I have bending moment and I have axial load, how can I compute the stress distribution in my member? Here, you have another scenario where bending moment can be coupled with a shear force. The cantilever beam presented here is an example of shear force plus couple developed at a certain section. In fact, the cantilever beam will support a transverse load at its free end. So if we represent it, this is a scheme represented the cantilever beam subjected to a force P at its extremity. Now, under the effect of this transverse load, if I want to know what is the type of internal forces and couples developed in my beam, I can just do a section. And from the analysis, I will get that from sum of forces along y equals 0, I will see that there is the need for of development of a shear force in the cross section to oppose the action of P. And also because P and P prime will create here a counterclockwise moment, the bending moment should be clockwise in order to ensure equilibrium. So this is an example where the type of stresses involved in my section is shear plus couple. So you can see that we can have different combinations of internal loadings. And in this chapter, we'll develop first what will be the stress distribution in the section resulting from pure bending. And after this, we can do the analysis for combined loading. Now, this is what we call the principle of superposition. So we can, if you want, decouple the two parts. So we can find what is the stress distribution due to the presence of an axial load. What is the pressure distribution, the stress distribution due of the application of pure bending, and then we can do the superposition of their effects to find what is the result of having uh, uh, bending moment and normal force on the stress distribution. Okay, so this is what we call principle of superposition. So the normal stress due to pure bending may be combined with the normal stress due to axial loading and shear stress due to shear loading to find the complete state of stress. Now, to start with, let us develop what is the stress distribution in a section that is subjected to pure bending. Okay, so for example here, if we consider the following structure and we apply on it at the ends opposite couples, then at any section, if we do any cut, we'll have just pure bending. For equilibrium, we should have in this section the development of a bending moment to oppose the extremity couple. So internal forces in any cross section are equivalent to a couple in this case, and the moment of the couple is called bending moment. From statics, a couple will consist of two equal and opposite forces. Therefore, the sum of the component of the forces in any direction will be 0, and sum of moments is the same about any axis perpendicular to the plane of the couple and 0 about any axis contained in the plane. You know from statics that whenever I have the moment is a vector and it's a vector perpendicular to the plane in which the moment is acting. Okay, so here, for example, if we consider the three directions, let's say this is Z, this is X, and this is Y. your bending moment, as you can see in this figure, is in plane YZ. So then your moment vector will be along X, and there is no moment developed in Z and Y directions. From this definition, okay, we'll be able to first do a general analysis of stress state and then relate the stress state to the case of pure bending. Okay, let us consider the most general case. So if we have a section and we want to know if you want type of stresses at any element of the section, so any small element can be subjected to shear forces, so shear stress, resulting shear stress, because you know that a shear force, so let's say an elementary force developed, dF, is equal to a shear stress times the elementary area, okay? So whenever you take a small element of your cross section, here the cross section is in plane YZ. So whenever I do a certain section, I have two directions of possible shear. Shear by definition is a force parallel to the section, okay? And in case in this 3D application, whenever I take a certain elementary area, I can have the development of shear stress parallel to Z, and I can have the development of shear stress parallel to Y. And you know already that whenever I want to refer to a certain shear, I can use two subscripts. The first subscript, so let's say when I say tau xz, when I say tau xz, the first subscript refers to the direction normal to the shear, and z refers to the direction of the shear. So here I have, this is tau xz, and along this direction, shear is along y, so this is tau xy, and the elementary shear force on this area will be tau xz times dA and tau xy times dA. Now, the other type of possible stresses is normal stress. Normal stress is perpendicular to the area, okay? And if it's acting outward, it's a tensile stress. If it's acting towards the section, it's a compressive stress. Okay, and it's called then sigma x. X refers to the direction of this normal stress, which is perpendicular to the cross section in plane YZ. So this is the general state, if you want, for a certain elementary area where we can see the development of shear stresses in two directions within the plane of the section and a normal stress perpendicular to the plane of the section. Now, in order to relate the stresses developed to the bending moment created along the surface, let us go back to the statics analysis. So for this, whenever you do this cross section, if you are in case of pure bending, if you do the sum of forces along the section is equal to 0, because in pure bending there is no developed force along X or along Y or along Z, okay? Because no shear forces and no normal forces. And Fx is due to what? So if we want to compute what how Fx can come from, a force developed in X is the integral of elementary force along X, and these elementary forces are due only to what? To the normal stresses. Okay, because the only force between the forces resulting from if you want internal stresses, which are the shear stress and normal stress, is the one along X, which is sigma x dA. So this is the elementary force dFx. So if you want to find in a certain problem what is the source of Fx, the source of Fx will be the normal stress along X. This is why we'll see after that in case you have, let's say, a certain normal stress, then this normal stress is developed from the elementary normal forces, which are calculated as integral of the Fx which is integral sigma x dA. But here, because there is no in pure bending, there is no net normal force, then you can say that integral sigma x dA for pure bending is equal to 0. Now, from this figure, what are forces along y directions? They result from elementary force dFy, which are due to shear stress along y. So dFy will be equal to tau xy dA. And if you want to find the total force Fy within your cross-sectional area, should integrate this term. So Fy is integral tau xy dA, and because it's pure bending, it's equal to 0 because no shear forces are developed in the cross-section. Finally, the same for Z. Any elementary force in Z is due to a shear stress along Z direction. So dFz will be equal to tau xz dA. And to find the total force along Z, we do integral tau xz dA, and which is in pure bending, it's equal to 0. Now, this is the force analysis from statics conditions of the sport. Now, if we want to do also sum of moments, okay, we can divide into 3 directions: moment vector component along x, along y, and along z. Since it's a pure bending problem, so you only have in this figure a moment developed along z. There is no moment along x and no moment along y. So the total moment along x will be equal to 0. The total moment along y will also be equal to 0. And we'll have only a total moment about z equal to the bending moment. Now, what are the contributors to these different component of moments? If we look at the general case, so here we are developing a general analysis and then applying it on a pure bending. So in general analysis, contributor to the moment about x will be shear stresses tau xz and tau xy. Why? Because if you look at this figure, if first the normal stress will not do any moment about x because it's parallel to x. And you know that to produce a moment, you need force components that are perpendicular to the axis. So here you have the first contributor to moment about x will be tau xz dA. This is the elementary force. And this elementary force will produce an elementary moment about x equal to tau xz dA times the distance between this elementary force and the axis x, and this distance is equal to y. Now, in order to know if it's plus or minus, you can do the right hand rule. Okay, if you apply the right hand rule, to remind you, the right hand rule, you put your four fingers of your right hand along the force. The palm of your hand is facing the axis about which you are finding the moment, which is here x, and then your thumb will indicate the direction of the moment. Here your thumb will indicate that the moment created by these forces is positive. This is why we put here plus y tau xz. And the other contributor to moment about x will be the forces along y. So the resulting from shear stress development in along y. So if this is an elementary force along y, it's equal to tau xy dA. And then if I look at this figure to determine the moment of this force, okay, about x-axis, I should consider the following distance, this one, which is the distance perpendicular, sorry, here. Yeah, this is the x-axis. So let me illustrate it if you want. If you do the extension of the force, you will see that the distance is this distance here, okay, which represents z of the element. Okay, so you will multiply dFy by distance z. Now To know if it's a positive or negative moment, also you apply the right hand rule. So you can put your four fingers along of your right hand along the Fy, the palm of your hand looking towards x-axis, your thumb will point towards negative x direction. This is why here you put minus z tau xy times dA. Okay, and because it's pure bending, the integral of this term will be equal to 0. Now, similarly, to determine what is the total moment about y, you look at this figure and you try to see what is the source of stresses that can lead to moment about y. First, if you consider shear stress tau xy, it's parallel to y, so the resulting force cannot produce any moment. Also, the shear force along z cannot produce here a moment about y, because as you can see, it's crossing, it's in the plane at yz, so it will intersect y and cannot produce a moment about it. So here's the only source for moment about y is the normal stress. So if I consider normal stress sigma x dA, so sigma x is the normal stress. When you multiply by dA, you get the elementary normal force dfx. And this force dfx can produce a moment about y. And to get the moment about y, you should look at the perpendicular distance to the force and to the axis, which will be along z. And from the right hand rule, if you apply the right hand rule here, okay, you will get that the moment of this force about y is positive. So you just put my is integral of plus z sigma x dA, and in pure bending should be equal to 0. Finally, for the moment about z, okay, similarly for moment about z, shear stresses along y, shear forces along y and z cannot produce any moment about z because shear forces along z are parallel to the axis, and shear forces along y are intersecting the axis, so no moment are created by these forces. You just have the moment created by the normal forces, and normal forces are due to the normal stress. So you have that elementary dfx, as we said, is equal to sigma x dA. And if you look at this figure, you are computing the moment about z axis. So you should multiply by the distance perpendicular to the force and to z, which will be along y. So you should multiply by y. Now from the following figure, you can see that applying the right hand rule, the moment of dfx is a negative. This is why you put integral of minus sigma x times y dA. And this is the only moment that is not equal to 0, because in the pure bending application here, you only have development of a moment vector along the axis. So you can say that mz is equal to the bending moment is equal to integral minus y sigma x dA. So you can deduce that the bending moment is developed due to a certain normal stress distribution. And our purpose is to develop the expression of this normal stress distribution. Now, let us continue the analysis of bending case. So let us consider a beam with a plane of symmetry in pure bending. In pure bending, the members will remain symmetric, because if you consider a part, a beam subjected to bending moments, it will undergo deformation, but the deformation will be symmetric with respect to the axis of symmetry of your beam. Okay, so the first observation of pure bending is that the member remains symmetric. Plus bends, we will observe bends uniform bends to form a circular arc. So as you can see, under the effect of bending moments, you will have in this example here, you have the upper part will be compressed, subjected to compression, and the lower part is subjected like to tension. This is why the upper part here will be reduced in length, the lower part will increase in length, And you have some, we'll see together that at a certain stage, we have a certain part that will not, for which the length will not be affected. Okay, this is called the neutral axis. The neutral axis length will remain the same during bending operation. Above the neutral axis, you will have compressive effect, so lengths of your parts will be reduced, and below the neutral axis, in this example, you will have lengths will increase. Of course, if you reverse the bending moment direction, everything will change. Then your center of curvature will be downward, and you will have the upper part that will undergo tension and the lower part that will undergo compression. So we say that in pure bending, bends uniformly we have to form a circular arc, and cross-sectional plane will passes through arc center and remains planar. So if you consider any cross-sectional plane, okay, it will always pass through the arc center and will remain planar. This means that this section will not undergo distortion. It will remain in one plane. Okay, and if you draw different planes, all of these planes will intersect at point C, which is the center of curvature of bending. Okay, so if you observe this arc of circle and also this arc of circle, their center will be the same one, which is the center of curvature of the bend. And all faces will keep 90 degrees angles after deformations. Okay, so if you observe your faces, they will not undergo variation in angle. This is why we can say that we don't have any shear strain developed. The shear strain in planes xy and xz will be equal to 0, and then this corresponds to 0 shear stresses in xy and xz. Okay, because all faces will keep their 90 degrees angle after deformation. So we don't have development of shear stresses in pure bending. We just have a development of normal stresses. Now, so if you continue the analysis of pure bending, we already said that there is no development of shear stresses, and we just have development of normal stresses that are perpendicular to the section. So there is no sigma y or sigma z. There is just sigma perpendicular to the section where which is undergoing the bending moment. So, and we'll see together that when we do the analysis of pure bending, we'll see that the length of the top surface will decrease when we have compressing couples like this. So the upper part length will decrease, the lower part, as we said, will increase, and we have a certain neutral surface existing between top and bottom that is parallel to the upper and lower surfaces, and for which the length does not change. Okay, so this is what we'll try to find. What is the location of the neutral axis and how it can help us into knowing the distribution of normal stresses in our section. So in the scenario presented in this figure, you have the bending moment is along z direction, and you can say then that in this case, in any cross section I take, the bending moment will be along z, and we'll try to find what is the normal stress distribution that will create this moment. So the surfaces above the neutral axis will undergo compression, as we said. This is why stresses and strains will be negative in these parts, and the surfaces below the neutral surface will undergo tension, where stresses and strains are positive. And if we reverse, as I said, if we reverse the bending moment action, everything will be reversed, and at the top you will have tension, at bottom you will have compression. Okay. Now, the next step will be to determine the neutral axis position. Let us take the following figure and do some interpretation in order to get an expression for the neutral axis. First, as we mentioned, we have like formation of arcs, and we have a common center for these arcs, which is called the center of curvature. And we have that above the neutral axis here, because you have bending in this like this. So here you are compressing the upper part. This is why the upper part will have reduction in length and the lower part will have an increase in length, while only you have one level at which the length will not change, which is called the neutral axis. So if we look at this figure, this is what we call the neutral axis. The neutral axis will keep its initial length. It will just undergo, if you want, a certain curvature, because it was straight first. Before applying the bending moment, it was a straight line. Whenever you apply the bending moments, it will undergo a certain curvature. But the total length at the level of neutral axis will not change. So this is my neutral axis. And I can say that the initial length is conserved for the neutral axis only, while for all other lines, they will undergo change in length. So above here, above the neutral axis, I have reduction in length. Below it, I have increase in length. And now I will try to relate, if you want, the strain developed, okay, tensile strain and compression strain to the variation of my length. Okay, so first let us consider a certain line. Let us consider first for the neutral axis. Okay, it's at a certain distance of rho from the center of curvature. Okay, so I can say that because the neutral axis is the only line that will not undergo change in length, this will allow me to compute what was the initial length of all my parts at the initial state. Because at the initial state, you had the following configuration. So at any section, the length is equal because you don't have a curvature. Okay. Now, when you apply a pure bending, the neutral axis will conserve its length. So because we can calculate from this figure what is the length of the neutral axis, since you know that an arc of circle length is calculated as the radius of curvature, which is defined as rho here, times the angle, the bending angle, theta, times theta. So the initial length of all my parts was L equal to rho times theta. Now, if I consider now part, let's say, any part at a certain distance from the neutral axis, okay? And I want to characterize the change in length of this part. So let us take this line here, JK, and we want to compute the length of JK, okay? To compute the length of this part, we just have to multiply the radius, which is CK, by the angle theta, okay? And as you can see, this radius can be calculated as the radius of curvature of the neutral axis minus y. We consider y, if you want, is the distance from the neutral axis to any level of interest, okay? So we take an origin, the origin as the neutral axis, and we consider y is the distance from the neutral axis to any level of interest. For example, if you are developing for any value of y, to compute the new lengths at y, we just do the radius, which is rho minus y times theta. So the final length of any part at a distance y from the neutral axis is rho minus y times theta. And this equation is valid for the upper and lower part. Because if you are below the neutral axis, y will be negative, and then rho minus y will be larger than rho, and you will get increase in length because the initial length is rho theta. When you are above the neutral axis, y is positive, and you have reduction in length. And when you go below the neutral axis, y is negative, so minus minus will give you plus, and you'll have increase in length. So now you can compute the change in length of any line of your beam, and therefore you can determine the deformation. You know that the deformation is calculated as the variation of the length. So for any line above or below the neutral axis, the expression of the final length is rho minus y times theta. However, the initial length is equal to the length of the neutral axis, which is rho theta. And then we can say that the deformation undergone by any line is equal to minus y theta. For y positive, you have a negative deformation, which is due to compressive effects. And for y negative, which is below the neutral axis, this will correspond to increase in length. So you will get a positive deformation. Okay. Now, by definition, what is the strain? Is the strain along x direction? The strain is defined as the deformation over the initial length. Okay, so it's the deformation expression is minus y theta, and the initial length is equal to the length of the at the neutral axis level, which is rho theta. So theta will be simplified, and we'll end up with the strain epsilon x is equal to minus y over rho. Okay, so as you can see here, you have a negative strain for above the neutral axis, and you have positive strain below it. And the maximum strain developed will be at your extremities, okay? Because you will have the farthest you are from the neutral axis, you will undergo a larger deformation, okay? So the maximum strain will correspond to the maximum distance from the neutral axis over rho. Now, we can find that if we just in this formula replace rho by, so from this equation, we can say that rho is equal to C over epsilon m. So if we replace rho by its expression in the equation of strain, we get that epsilon x is equal to minus y over C times epsilon m. This means that the variation of strain is linear, okay, because it's a function of y. So it's a constant times y. So you have linear variation of the strain within your cross section. And this is a very important result because if the strain is varying linearly, then the normal stress also will vary in a linear way. Why? Because we know from previous chapters how to relate normal stress to strain. You know that for a linearly elastic material, the relation between normal stress and strain is given by sigma x equals the modulus of elasticity times the strain along x. And then if you replace the strain by its expression, which is minus y over c times epsilon m, and you know that the value of epsilon m times modulus of elasticity is sigma maximum, okay, then you will get that your normal stress variation with respect to y is linear. As expected, you have it will be equal to 0 at the neutral axis, and then above the neutral axis here you will have compressive effects, so you will get a negative result. So if you want to illustrate your stresses, you have compressive stresses above your neutral axis and tensile stresses below it, because below it you have y negative, minus minus is plus. So you will have the development of tensile stresses below the neutral axis. And then the net, if you do the net moment created by these normal stresses, you will have a bending moment along Z. Okay, so we can now say that the normal stress distribution will be linear and it will be zero at the neutral surface. So if we go back to the equilibrium condition, that f of x is equal to zero, and we replace sigma x by the expression we derived now, which is minus y over c sigma m, then we deduce that the condition of equilibrium along x is that integral minus y over c sigma m dA is equal to zero. Since sigma m and c are constants, we can take them outside of the integral, and the result is that integral y dA should be equal to zero. And you know that this is the definition for calculation of the centroid. Okay, you can replace integral y dA by a times y bar, which is the centroid position of the area along y. This should be equal to zero. This means that y bar is zero. And this will tell you that because your origin is at the neutral surface, since y bar is equal to zero, this means that your neutral axis should pass by the centroid of your section. So this analysis allowed us to determine the neutral axis position. The neutral axis should pass by the centroid of our section, okay? And the normal stress distribution is a linear distribution, and it will result into the creation of a bending moment. Now, this integral y dA is called the first moment, and the first moment with respect to the neutral axis is zero. And this is an indication that the neutral surface must pass through the section centroid. So we were able to locate the neutral surface, and we're able to locate we're able to develop the variation of normal stress across our section. So to summarize, as we can see in this figure, we have developed the general expression for normal stress, how it's varying with y. It's a linear variation. It's zero at the centroid, which is the level at which we have the neutral surface. And the total bending moment will be resulting from integral, as we have seen before. The bending moment is integral of minus y sigma x dA, replacing now sigma x by the expression we developed together in previous slides. Sigma x was found to be minus y over c sigma m dA. And since sigma m over c is a constant, we can take it outside of the integral. Then the bending moment in pure bending application can be computed as the maximum stress over C, which is the farthest distance from the neutral axis, times integral y squared dA. This term, okay, is called, so this is the second moment, okay, and it's called the moment of inertia or second moment of the cross section. So we can say that the bending moment can be expressed as the maximum normal stress times the moment of inertia I, about, of course, the neutral axis, over C. And we'll learn together how to determine I. So this formula, if we know the bending moment value And of course, knowing the geometry of the cross section, we can get the value of I. This will allow us to determine what is the maximum developed stress in our cross section. Okay, so let us consider the following case. Just in summary, these are the main formulas we developed until now. We have that the value of the maximum stress developed will depend on the moment of inertia, which is integral y squared dA. These inertias are depending on the geometry of the cross section. So each cross section geometry will be characterized by a formula for I. For example, if you have a rectangle, and the neutral axis is passing, of course, by its centroid. This is the neutral axis. The inertia about the neutral axis, if we know the dimensions A parallel to the neutral axis and B perpendicular to the neutral axis, we can say that the inertia about the neutral axis is I equal to AB cube over 12. Okay, and each geometry has a certain formula for I. So you have a formula for a triangular cross section, you have another formula for a square cross section, for circular cross section, etc. Each cross section is characterized by its formula of inertia. Now, if we define what is called as the elastic section modulus, we have S is defined as the inertia, the moment of inertia about the neutral axis over C, where C is the farthest distance of the cross section from the neutral axis. Okay, so for example, if we take the rectangular part, the farthest point from the neutral axis is at a distance of b over 2. So in this case, C is equal to b over 2. Okay, now we define the elastic section modulus as I over C. Then we can say that the maximum developed normal stress is computed from MC over I, or if we replace I over C by S, then the maximum stress is M over S. And in order to reduce the maximum normal stress in your section, you have two possible strategies. You can try to decrease the bending moment, or you can try to increase S. And to increase S, you can or reduce the moment of inertia, okay, or increase the value of C, which is the farthest distance from the neutral axis. Okay, now sigma x at any location can be computed function of sigma m. We have that sigma x is varying in a linear way with respect to y and is given by minus y over c sigma m. Okay, now we can then apply this result, for example, on the following case. Let's say we want to decide on which cross section is better for a certain application. In general, you know that you try to reduce your maximum stresses because each material is characterized by a maximum normal stress it can sustain. And if we exceed the stress, we'll have rupture. So to avoid any failure of our structures, we need to do a good design and try to reduce the maximum normal stress, and of course to be below the maximum allowable stress. Okay, so here, for example, we have developed together that the maximum stress is given by M over S. So if we have a certain load, we are restricted to a certain type of load, the bending moment will be imposed. So what we can do, we can change the geometry of the cross section in a way to increase S for reduction of the maximum developed stress. And to do so, we go back to the expression of S. So from expression of S, let us develop for a rectangular cross section what will be S. So as we mentioned before, if you have a rectangular cross section, the neutral axis will pass by the centroid, and you have, let's say, B is the dimension that is parallel to the neutral axis, H is the dimension that's perpendicular to it, then the inertia about this neutral axis will be given by B times H cube over 12. And as we mentioned also, C is the farthest distance between the neutral axis and the cross section. Here, if you want, C1 and C2 are equal. So C is equal or C1 or C2. In some cases, they can be different. So you'll take the largest one between the two. So here, C is equal to just half of H over 2. So if I replace in my formula here, and I simplify H, so I have H here and H cubed, we get H squared, and 2 over 12 will be 1 over 6. So we have that S is 1 over 6 BH squared. So it's 1 over 6, the area is B times H for a rectangular cross section. So it's 1 over 6, the area of the rectangular cross section times its height. So you can deduce that for the same cross-sectional area, okay, a better design will be to have a larger height, because a larger height will induce a larger value of S, which will correspond to a smaller value of the maximum stress. So for the same area, if you have to select between these two sections, you will select this one because it will ensure a lower maximum stress developed in your section in case of pure bending. Okay. So between two beams with the same cross-sectional area, the beam with the greater depth will be more effective in resisting bending. Structural steel beams are designed to have a large section modulus in order to reduce the maximum normal stress. Now, let us consider the expression of deformation due to bending. So we already developed together the geometry of bend. We said that we have only the neutral axis, which will will not undergo a change in length, and we can calculate the radius of curvature of the neutral axis. We want its named rho, and we want to compute its value. So we already developed a previous relation between the length of the neutral axis and the value of rho. We said that L is equal to rho times theta. Okay, and we have that the deformation of the member by the bending moment arm can be measured by the radius of curvature rho, and it's equal, this radius of curvature is computed as 1 over rho equal to epsilon m over c. So rho is equal to c over epsilon m.